So next we have today 11 o'clock. We have scheduled 11 o'clock, but we are a little early, probably. So I introduce John V. Kennedy. He is our alumni, department alumni, and he was a student of this department from 1994 to 1999. So he was has carried out his PhD work under Dr. Agasti, Department of Physics, and carried out the work at IGCAR Kalpakam during 94-99. And after that, he had postdoctoral fellowship at Notre Dame University in Belgium, and from there he moved to CNRS in France for another postdoc, and after that, I think 1 year he's at 2001 onwards, he is in GNS in New Zealand, which predominantly it's a nuclear and material lab, and GNS stands for Geological and Nuclear Science. So I think the Institute of Geological and Nuclear Science, and they call it GNS Science. And presently, he is the principal scientist, research leader, Advanced Materials and Nanotechnology, National Isotope Center, GNS Science. And he has, to his credit, he has 262 articles with 6,577 citations with a H index of 51, and he's been honorary professor at University of Waikato, Hamilton, and also in Singapore. He is part of Nanyang Technological University, Singapore. So sorry for that. So he is at present he is scientist at this principal scientist at Advanced Materials and Nanotechnology for the last 10 years, and he will be speaking on these cutting edge technologies, and which has more relevance to radiation, along with developing new materials and energy solutions and other things. And it will be the somehow an eye opener for ourselves. Maybe those who want to share the research with technological development for the industry. So they have very good collaboration, as I understand, that they have a good collaboration with the industry groups, and they are doing a lot of new activities. So probably this is our researchers will take a leaf out of their research activities, and I hope this will be very good for those who are working in material science as well as in radiation effects of materials. So on behalf of the department, I am very happy to invite John Kennedy for this talk. John, please.
Thank you, Professor. I think I should share the screen. Do you see the screen? Do you see the screen?
Yeah, it is visible. Yeah, but voice have some problem.
What about now? Is it better now? Can you hear me better?
Yeah, it is. There is some echo.
Oh, it's echo. Okay.
Okay, now it's okay.
Okay. Very good morning, everyone. My fellow Indians, greetings from Wellington, New Zealand. And as you can see
in the picture. It's a beautiful country. I'm sure you all know very well. It for us, just spring has just started, and you can see at 5 p.m. the sun is still there. It's quite unusual because we just finished the winter, and you can see the snows are still there in the mountains. So I'm a principal scientist and the leader of the material science and engineering group in GNS Science, which is a Crown Research Institute, which is equal to your Department of Atomic Energy in India. So we are government research institute. We are owned by the government, and we look after the geological and nuclear science related activities for the government of New Zealand. That means we look after the earthquake. As you probably know, New Zealand is well known for earthquake and volcanology and occasionally tsunamis in the past. So we do run a group of people looking at the earthquakes prediction and risk mitigations. And we also look after the landslides. And then we have a nuclear science division where we traditionally used to do a lot of isotope science and particle accelerator physics later. But in modern times, things are changed. Now we are focusing more on material science and manufacturing using nuclear instrumentations. So that's where our core research activities are focused now. Being impact-driven institute, every research direction we review every 5 years and has to focus by the near to long-term impact-driven portfolios. So this is, we do have universities. We have 6-7 universities in New Zealand, so we work with them closely. I run initiated a program which I was funded during my PhD days, Inter-University Consortium, which is in nucleus IUCAR Delhi. I don't know what's the name now. So I run a similar program by supporting my local university students and researchers. So as Vinod said, I did my PhD at Calicut I think 95, 99, towards the end of 94, and submitted thesis in June 1998, and graduated in February 99. So that was part of Inter-University Consortium Scholarship. I was stationed at IGCAR Kalpakkam. So I probably visited Calicut 2 times, 3 times, probably the whole 3 years. Before I start my next conversation, I must thank Professor Agasti and Professor K.M. Warrior, who are the experts in the field I did my PhD, which is called a PIXI, particle-induced X-ray emission, which we use to demonstrate elemental profiling, quantitative elemental analysis of river water sample. I think it's the Chalia River, if I remember correctly. So Professor Warrior and Agassi used to help me a lot to understand the soil dynamics, get the details of the soil dynamics in Chalia River, and also link with the X-rays and gamma rays. Vinod is also did the PhD at the same time, so I remember Vinod very well, and I remember Dr. Anthony Joseph as well, who used to be with the same group. So even though I was attached to Calicut University, but I used to interact with Warriors most of the time regularly, and Warriors used to come to Kalpakkam and spend some time and look at my data and provide feedback. I thoroughly enjoyed because he did a similar work when he was in IIT Kanpur. So I was benefited more from the fundamental perspective of how the X-ray cross-section, inner cell X-ray, coastal X-rays happens, and all those things. You know, when you are a student, you're always keen to know the basics of it. So that's what I did. I forgot to mention that I was graduated from Loyola College, Chennai. So I'm basically a Catholic a boarding school boy. I was born and brought up in a city called Karaikudi, something near, I think it's near Madurai, if you want to put it in the context. and grown up in a Catholic boarding school and went up to masters in Loyola College in Chennai. Then I went to PhD. So that's how my life was. So then after a PhD, like said, I even think Warrior sir knows very well. I was one of those lucky people got a postdoc before you submit a thesis. I'm just saying this context is there because I believe there are quite a few PhD students and master students attending this seminar. So the reason I say is I had opportunity to submit an abstract to an international conference in ion beam analysis in PIXI, later ion beam analysis work in Sweden. So I did submit abstract based on my second year of work research results, which is not outstanding, but it's basically summarizes new finding. Then I got the paper was accepted, abstract was accepted. They even waived the registration fee, and they asked me to come and present it. I was lucky enough to be supported by the Department of Atomic Energy that time to pay for the trip and go to attend the conference. So I went there to Sweden to present actually the PIXI analysis of Chalia River. That paper, various are still cited around 20 times. It's one of my very best PIXI paper, which is Calicut University's affiliation. I think it's probably 20 or 50 times. I can't even remember now. So I went there as a young man, as you can imagine, when you get a chance to go to overseas conference to present your second years of PhD work, why not? So I went to the PIXI conference and I gave a talk. Obviously, nervous is everything because you never seen the flight before. You jumped in the plane and alone, and that journey is always memorable journey from Chennai to London, London to Sweden. Anyway, so during the conference, I gave a talk on the PIXI. Then as soon as my talk finished, there was a coffee break, and then professor from Belgium came and talked to me. Hi, John, do you like to join our group? And said, okay. Said, I am, how long you close to PhD? I said, another year. No, go and write the thesis and submit and come back and join us. So what it tells you that it's all about how you convey the message, but what you learned. He was so impressed. He told me, what made you to choose? He said, no, I can see I know what you are talking. I can see that you know what you are talking, and you're able to explain the basics to the application side. And he just offered me a postdoc. So this is a very good examples of how PhD students need to understand the subject carefully and also able to explain it to others in a way, an expert, not a layman, because Professor was working in the similar field, and he was able to see that I have something to offer, something new to offer. You have to remember that in modern times, people will not employ you because they need another workforce. They need to learn something from you. They need to see that something you are bringing to the table. And that's the thing that happened to me in those days. And that had changed all my life, as you can see. So then I then I also got another offer from Japan on the same symposium, same conference, and US. So we got 5 offers basically. So then went back and submitted a thesis and move on. So then I did a postdoc in Belgium looking at completely different area, how to apply the nuclear intimidations to material modifications and to make some new alloys for manufacturing industry. So I learned completely different way of applying ion beams, we call it from nuclear physics, to a new area. So during my 1 year of postdoc, then there was again another meeting in the European Union because I was funded by the European Union, and somebody came from New Zealand, and because New Zealand is still a kind of European colony, Queen is still our in charge. So he was impressed during the meeting, and he said, do you want to come to New Zealand? And we offer you a permanent job. I said, fine, I'm still single and 27 years old, and you got a permanent job in overseas? Bingo. That's what happens. I said, okay. I honestly asked that, where is New Zealand? Because I didn't know New Zealand before. And they liked my honesty. Saying, I said, then they explained to me, I said, yeah, I know New Zealand plays cricket, but I don't know where they're located. So that was the kind of, I hope you're hearing me. Vinod, correct? Vinod?
Yes.
Yeah.
Yes.
Sorry.
No
Yeah.
problem. No
Yeah.
problem. Go ahead.
Please tell me if you're not hearing me, because I don't know, correct?
So we can hear it. It's very interesting.
Yeah. So then I said, okay, I will come. So I then obviously, as in traditional Indian children, I asked my parents to arrange a marriage. Then they arranged a marriage, came to Tamil Nadu and went to stay a month, got married, and we both came back in Jan 2001. And to join GNS, as I said before, it's a government institute. I joined as a normal scientist 1, which some of the government people know. Now I am the principal scientist, which is our topmost career position in this place. And I'm also the group manager for the National Isotope Center. So that's how the journey. And again, the reason I said the journey again, it's because even though my PhD was slightly different application, but during the 1 and 2 years postdoc, I was able to articulate where else you can apply nuclear instrumentation, what impact it can make in the manufacturing sector. So then that's the reason I end up landed here, and I started this restructure the whole nuclear instrumentation group to focus on impact-driven manufacturing and materials research. So that's my key role. I'm also a principal investigator in McDermott Institute. Some of you, which is a center of excellence, it's a center of research excellence for advanced materials nanotechnology. Some of you know who is McDermott, Alan McDermott, who got a Nobel Prize in conducting polymer in 2000. In 2002, he's a New Zealander. So he was born in next to my this town where I live in. So we started the Center of Excellence 10 years ago. I mean, you know, when you have a Nobel Prize winner, it's easy to convince the government to give huge funding to start a research center. And so that's, and 2000, early 2000 is nanotechnology is high flag. So we managed to convince the government to start a new virtual center where the principal investigator from experts from every key universities and government labs, where the top experts join as a group and do some fundamental science in advanced materials nanotechnology. So I'm still continuing that. That's why we take PhD students and postdocs. In fact, currently I have a student from ARIA who's from Calicut affiliated college. I think I forgot the town somewhere between Coimbatore to Calicut. I forgot the name town. Anyway, so she comes from there. So she's the current PhD student as well. So that's where we support PhD students. I also am the principal investigator in New Zealand Product Accelerator, which actually we work with industries. So we have 250 manufacturing companies where we liaise with them to understand their day-to-day need. Then we basically tune some of our research direction and to make some prototype product portfolio for the companies. So I lead the initiative for the whole manufacturing industries. We have people working from all the universities nearby. But the point is, this is similar to, I said, IUCA, Inter-University Consortium, where it's done for research, but here I run the consortium for industry. So this is how our research activity goes on. And as I said, being a developed country and also being a small country, and as you know, it's only 5 million population, our public is well aware of, we have very good knowledge. Everything we do, we have to be answering to the public. And we have a community which can question you at any time. And you should be able to answer because it's a taxpayers funded. We have a very pragmatic and open community, a completely transparent system. As you know, New Zealand is the #1 corruption-free country in the world. Next to Finland, sorry, now #2. I mean, Finland and they each actually equally #1. So it's a complete transparent system, which is the reason why I stayed back. Now I'm completing the 20 years and soon. So everything we do, we should be answerable to public. So that includes research. So every research direction we decide, we go for it, we quite often struggle. And you will see during my presentations how even a physicist can actually do something useful for societies, not only doing fundamental science. So I'll give you some examples on that. Moving on, as you know, in modern times, the biggest challenge for us is the climate change. Global warming is there, 1.5 degrees C. And as you know, the IPCC panel has clearly highlighted that we have to reduce the carbon emissions. So we have to dramatically reduce the global net carbon emissions to have a climate change under control. Otherwise, our future is under really under disaster. So this is one of the modern days of challenges. So we need to see how we can come up with the technologies to support mitigating CO. I mean, to support reducing carbon emissions. As you know, these days, what is important is low carbon energy, and that's where the whole world is moving. And that's probably the only way you can actually deal with the climate change. You know, currently, most of the energy production is 2/3 of global is greenhouse gas emission, because either they produce from coal or burning oil and stuff like that. That is a huge CO2 coming. So according to the prediction says by 2050, you have to reduce 85% of this, which means you need to go find an energy source which doesn't produce CO, I mean, doesn't emit CO2. So obviously renewables energy is the way to go. And yes, solar is the one. But New Zealand, it's 95% renewable energy. Our energy comes from hydro, wind, geothermal, and very little solar, because we don't get much sun here. Our summer temperature is maximum 24, as you can imagine. So, and winter, most of the time, average temperature is 12 degree and 13 degree, like that. So it's a really low temperature, but we still have some radiator heat. So we use 2 to 3%, we generate solar. But other countries, it's very important to move to renewable energy source. So that's the only way you can avoid the catastrophic climate change, which is going to come. Believe it or not, it's going to happen. And we do even run our own Antarctica Research Center here, where we monitor the ice core melting. We have a base in Antarctica here, which is not far away, by the way. The flight from here to Antarctica is 5 to 6 hours. That's it. So we are very close to southern Antarctica. So we understand, we do routine monitoring of ice cores. We bring it here, we look at the isotopes to look at the carbon, oxygen, hydrogen ratios. Then we can coordinate how many years old and what's happening in terms of the lifetime. So climate change, it's a challenge. And of course, renewable energy is it's solar and wind. And countries like India, solar and nuclear has got different issues. So and we're relying on, and people are now moving more towards the even hydrogen, which is another area we operate. I also lead the hydrogen technology platform for New Zealand, but I'm not talking in this context here today. But that's even we are moving to green hydrogen. So hydrogen produced using the water electrolyzer, the electricity comes from the hydro. So that's called green hydrogen. So we are going towards the future.
John? John? There's some echo.
Still getting it now?
No, it's not clear.
Okay, I'll
Still.
change the headset. I'll change the headset and see whether that goes.
Oh.
Okay, give me a minute.
Hello? Hello?
Is it now better? Can you hear me now?
Yeah, it's better.
Ah,
Yeah,
okay.
fine now. But your presentation,
And can you hear me now?
yeah, it's okay.
Can you
We
hear
can
me
hear
now?
you. Yeah, sure,
Yeah.
no problem.
Okay. Now I carry on. I'll put the presentation back again. Can you hear me? Can you see my presentation now?
No, there is audio problem.
Yeah, it's okay.
No, it's okay. You can see my presentation as well, right?
Yeah, but low voice.
Audio is feeble.
Okay, that's interesting.
Yeah, presentation you can see. Yes,
Now,
no problem.
no problem.
No
Okay.
problem.
So
Go ahead.
So that's where the whole world is moving towards the low carbon energy technologies to avoid the catastrophic climate change. So as you know, the energy alternatives, as I said before, you have a fossil fuels, you have nuclear, and hopefully the future we will have even fusion reactors. So that's all. So the renewable is a key area where most of the research could be done, could be improved, and could bring some mitigating factor for climate change. So the energy gap is growing, as you see. By 2050, we need 14 terawatt, but that means if you take 10 terawatt, 10,000 gigawatt, that means you need one new power plant for every day for next 27 years which is not practical. So there are many. You have to find alternative ways of generating electricity, of energy, rather than relying on one single source. So this is why, rather than worrying about how to make more energy by nuclear and fossil fuels, why don't we harvest energy? So energy harvesting is another way of. It's a great tool because it can address the issue of the climate change in a different way. Because it takes you reuse the ambient energy, which is otherwise wasted. So this is energy harvesting. Conceptually, it's not new, but what happened in the past is people ignored it because it doesn't really give much efficiency and much impact. But when people start thinking about the nature and the impact of the climate change, every percentage of improvement matters. So energy harvesting matters, and it is going to have a significant impact in the climate change as well. There are many ways energy harvesting is done. As you know, you can harvest mechanical energy, thermal energy. Obviously, solar radiation is the solar cells. So in the literature, you can see there is this table summarizes nicely what are the harvesting methods and what operational mode they operate, whether it's a photoelectric effect or piezoelectric effect or photovoltaic effect or Faraday effect. So these are you all studied in your textbook, so this is nothing new. But what it gives you, this is also gives you the power density, what maximum power you can achieve. So the efficiency is a challenge, as I said before, it's an ongoing challenge. Having said that, because every improvement, even 1 or 2% improvement, if we convert it into the power density in terms of the environmental and societal impact, it does add value. So you have to look at it in a broader perspective. It's not only for making money, it's more about sustainable future perspective as well. So if you put in a different context, currently, if you look at the key energy harvesting market, thermoelectric stays 46%, still the biggest energy harvesting method used globally to harvest the waste energy. Then piezoelectric and other things as well. Photovoltaic is picking up, it's going rapidly. I think this is only until 2018. So now you can imagine the PV is more than 12%. It's slowly ramping up, and that is going to significantly make big changes to this. So today my talk will be more focusing on thermoelectric, and the reason I picked up thermoelectric is because it is physics-driven concept, and because this is a physics department seminar, I picked up thermoelectric rather than hydrogen, because we also do quite a lot of work on green hydrogen production, storage, and transport. So I thought there would be more students attending, so it's better to go with a bit of basics and introduce some new findings and new applications. So as you all know, thermoelectrics is not new. It has been used many years in NASA for satellites to power some of the small components, and it's also, there's quite a few thermoelectric generators. It's been used in remote areas. So it's been going on years to see whether we can take the waste heat and convert it to electrical energy. And it's still going, and always the biggest challenge is efficiency. So I'll come to the point later on why energy efficiency why thermoelectric efficiency matters, what influencing them, what can you do as a physicist, what can you do as a material scientist. So if you're putting in a context a thermoelectric engine, if you look at the diagram A, when current is run across thermoelectric junction, when you say junction, you need a P type, N type. I think we all studied in your textbook. So it heats or cools through Peltier effect, depending on the direction of the current flow. And you know that it's again, this is something we studied, and sometimes we don't think, we write in exam and pass it, sometimes we think why it does. So depending on the heat flows across junction, the electrical current is generated through Seebeck effect. It's a cool one. So this is how but then when you go to practical thermoelectric generators, and a large number of junctions in a series, then you generate operating voltage wide across the heat spread. So that's how it is done. So it is being done, and it's still being improved, and still ongoing challenges in terms of the efficiency. What you see here is a still PN junction, a typical semiconductor physics. And that's all we are talking about here. And if you even go into the thermodynamic cycle, if you go even, how does a thermal generator operates in a big environment, you have a kind of, you can take a temperature gradient along the engines. You know this, if you look at the automobiles or something, the engines, you have the gap. Sometimes you have a controlled air and sometimes uncontrolled air, and you have combustion process. You can see how much heat is come through and how you can capture them. So that's how it is done. So as you see, in here, there is so much energy is lost as a waste heat compared to even total energy consumption. It is predicted that around 60% of the energy is lost as a heat into environment through various power plants, automobiles, and manufacturing plants. It's a huge list. People ignore it because there is some people ignore the rules and regulations and policies. Some people have a difficult design. It's hard to put a harvester there to capture it. Again, it's done because of the economics. One of the reasons most of the time people ignore it is also economics. So that's challenged the material scientists to come up with the new technologies and new materials which can efficiently recover the waste heat into electricity. So I call them capturing a free lunch. It is free lunch because it goes in the environment. So we starting to look at thermoelectric power generators will probably be a simple solution to recover the waste heat in many environments, many scenarios. As you can see when I go through, because it has got a no moving part. It's a direct energy conversion. You convert heat into electrical energy. There is no pollution involved. And you can power them self-power them. And you can see in the right side some of the designs, how people have even used the thermoelectric elements, how the heat is injected or rejected, and how it's converted to voltage. There are a lot of interesting, enthusiastic research done in, you can even, because you know that our body generates heat, and you can actually harvest some few volts in you having thermoelectric element in your t-shirt, and you can actually, people have done quite a smart work. Even you can basically produce enough 2 volt to charge your iPad. So so there is so much is possible. That's called wearable thermoelectric generators, and it's been used in wireless sensors and biomedical devices, even in the fuel cells, biofuel cells. And recently this Internet of Things, all the IoT sensors are self-powered by thermoelectrics as well, most of them. So it's easy to make 1 or 2 voltage, but we are after bigger than that. So what I'm going to continue is to touch base some of the basics of it. What is thermoelectric? And as you know, it's a direct conversion of a temperature difference to electrical voltage, and you can go other way around as well. So the efficiency of the thermoelectric materials depends on a figure of merit, which is alpha sigma squared T by K, as you know. It's a Seebeck effect, it's a Seebeck efficient square, electrical conductivity, and at a particular temperature divided by thermal conductivity. It's simple equation we all studied. And you can imagine the challenges by looking at it. The electrical conductivity doesn't necessarily directly proportional to the Seebeck coefficient. So you'll have to see. And the thermal conductivity is another phenomena which is scattered, depends on many things. So moving on, if you look at the, Seebeck effect is looking at the potential difference. Peltier is the cooling. And there is another one called Thomson effect, which we all studied to absorb and evolve the heat as well. So this is nothing new. Our pioneers have done it in 1827. That's where the Seebeck is proposed this famous formula to look at the energy per charge carrier from hot to cold. However, now, as I said before, efficiency is a factor. So what can we do? It's a simple sigma square, Seebeck squared conductivity and times thermal conductivity. In the early days, and I think until 90s or 2000s, a lot of research has been done looking at the thermal conductivity because it's inversely proportional, because you divide the division factor. So they did a lot of work on how to reduce the thermal conductivity by thermal conductivity is actually depends on whether it's a lattice thermal conductivity or electronic thermal conductivity. Then people did a lot of work on looking at the phonon group, which can influence the lattice thermal conductivity and the specific heat. So then they went down and did a lot of theoretical work and experimental work to prove whether it depends on the elastic constants or it depends on the fundamental defects of the materials, or maybe the grain boundary effect, which can influence this thermal conductivity. So that's been heavily researched, and now we reach the point that there's nothing much you can do, because we studied in amorphous materials, crystalline materials, and polycrystalline materials. So, but the other two factors are still possible because they are semiconductor driven base. It's a Seebeck coefficient and electrical conductivity. And if I tell you in terms of the band diagram, the Seebeck coefficient is basically you got to reduce Fermi potential basically, and you have to depend on the scattering happens in the energy level, and also you have transport coefficients. Then again, if you put in our solid state physics Kittel context, you look at the density of states, then you see, okay, maybe the effective mass of the particular element needs to be tuned. And then the mobility comes in, because when you add too much number of electrons, then the other things change as well. So, however, this is a kind of place where the more and more new technologies technologies coming up to fine-tune the number of carrier concentrations in a very minute level. We believe we can make some improvement on the efficiency by tuning manipulating number of electrons and charge carriers and basically density of state on this, which can contribute to Seeber coefficient and electrical conductivity. Everything okay, Vinod?
Yeah, it's okay.
Yeah. So let's look at what are the materials studied so far. So it started in 1950s. People have looked at the lead telluride and bismuth telluride, and still bismuth telluride is the highest efficient materials. And you can see basically the roadmap. In 60s, and as many materials came, and people are looking at the bulk side, and they're slowly, still ongoing challenge because it's a complicated crystal structures, and also the defects and the way the atoms are oriented, it's complicated to tune them. So that's why there is a lot of research has been done, and now still we are moving into more on some sort of topological insulators and semi-conducting materials, and also some heavy organic, inorganic kind of core-dope materials as well. So this just gives you a rough overview of, even though the physics is simple, but in the modern times, there are other challenges when you want to improve the efficiency of the basically ZT. So just this gives you a nice overview of what has been done in terms of the figure of merit and ZT. You can see that most of the bulk inorganic systems achieved over time. That's the A, and highlighting diversity of systems and mechanisms shown. The B side is the one where we can now some organic materials, organic inorganic hybrid systems are coming up, where people are looking at to see whether we can, because they're cheap and easy, abundant materials. But you can look at that diagram P, the efficiency is far lower than that diagram A. That tells you it's a long way to go ahead, because bismuth telluride is efficient. I mean, ZT is 1, which is the one first commercialized, and you can even buy it now, which is the one used in NASA satellite as well. But now, over the years, now you can go to even other materials which can go figure out merit up to 2. So this is a typical challenging problem for physicists and material scientists to address it. So, so what are the strategies you can enhance the Seeber coefficient? As I said, Seeber coefficient is squared, so it does play a bigger role. And you can see there, and it's completely depends on the density of states and the effective mass carrier concentration M star. Because if you look at this formula, M star is which is called effective mass concentration. That is due to the band flattening and band conversions. I mean, I'm going too much into solid-state physics, but as you can see, you can still do a lot of theoretical calculation to understand whether we can do something about it. The beauty is now artificial intelligence, AI, machine learning, is actually helping us to identify some of the materials by incorporating these parameters as well. So there is a work we just started. It's a huge international collaboration. We started and see how AI can actually help us to combine a few materials and to get this efficiency factor high. That's coming up. So the technology is helping to understand better, at the same time come up with alternative way of improving the efficiency. And as I said, the phonon coupling it's one of the things which heavily done. You can see in the organic materials, the electron phonon coupling, the extent where it is spatially energetically disordered in organic materials, hybrid materials, it's amorphous or semi-crystalline. If you look at the temperature, which is sigma and Seebeck, it's going up, and at some point it's going up on some cases as well. When it's amorphous materials, keep on going up. So that gives you a rough idea. All right. So this actually came from the machine learning. Yeah, applying AI to predict what are the ways it can go. So this publication came recently, one of my collaborators group. So in a nutshell, as I said before, the early days people worked on looking at the thermal conductivity, looking at the lattice and electron phonon interactions, and every scale, even atomic scale, in nanoscale, at sub-micro scale, you name it. It's because lattice thermal conductivity depends on multi-scale phonon scattering, and every material has got intrinsic thermal conductivity. So when you do some kind of tuning, either defects or if you create more dislocations, then you obviously can tune the thermal conductivity as well. So this is a kind of overview of what is happening rest of the world on this thermoelectric efficiency journey, and what are the complications. So what motivated us to do? We, as a ion beam physics based materials science team, we have been looking at closely the figure of merit and what can we do. If you look at the diagram, the carrier concentration, I mean the alpha, which is the goes straight up. I mean, alpha goes down when sigma goes up. So, and the thermal conductivity goes up if the carrier concentration goes up, but the alpha goes down. So you have to find a gap, place where you can balance everything. You can optimize the carrier concentration. You can also have the alpha and sigma reasonable level so that your figure of merit goes. What it means is you should be able to tune the electrical conductivity and the effective mass carrier, which means you can look at the number of electrons, and also you can do some doping strategies to do that. So because the electrical conductivity is Ne mu, you have a mobility and the number of electrons as well. So we didn't touch the thermal conductivity because it's very much known. We looked at mostly tuning the electrical conductivity and the Seeber coefficient. So this is the two parameters we thought let's have a go at it, right? Because you can actually make amorphous materials and polycrystalline and crystalline as well. So we concentrate most of our work. So I'll give you 3 case studies because of time. So we looked at bismuth antimony telluride and zinc antimony, zinc oxides, which is aluminum doped zinc oxide, and new materials called copper iodide. So how do we make our thin films? We use a technique called ion beam sputtering. What it does is you have a sputter target. Let's say you want to make zinc oxide. You put it 15 kV argon ion beam. Ion beam is generated from ion source. It's simple RF ion source. You have anode and cathode. You form RF plasma. Then you generate, let's say, a milliamp current. You hit that target. You sputter them. Then you have a substrate as a catcher. You catch it as a flame. It's simple as that. This is the technique came out of our basic nuclear instrumentation, as I said before. This is something I patented in 2011, and we have been doing quite a lot of work on this. You can make thin films of amorphous, polycrystalline, and also crystalline if you heat the substrate as well. So this is the technique we use in our lab to make thin films, and it's a simple one, and everybody is easy to operate. It operates in minus. We have a thermomolecular form, so you can see it's high pressure. But we also have an in-situ gas feed system as well, option as well. If you want to sputter it under the nitrogen atmosphere or some specific argon atmosphere like that. So this is the one which we use, and you can see the films you can deposit in any substrate. There is no problem with that. And so why bismuth antimony telluride? As I said there, the head structure and the perimeter cell. The biggest advantage is their narrow band gap semiconductor. So which gives the biggest advantage in this case. So if you look at the crystal structure, you have a tellurium is in a 1s vacancy, tellurium bismuth is an andesite as well, which is kind of tells you that maybe you can manipulate the lattice and andesite locations of these materials and change the crystal geometry, and you can create a bit more vacancies and see what happens in terms of the conductivity. So we looked at it carefully. We made a thin films of it, and I used my nuclear physics technique, RBS, Rutherford backscatter spectrometry, which is done by Professor Warriors when he was in IIT Kanpur. So this is the same old technique, which is 30, 40 years now. And this is something I learned in Kalpakkam, and I still use it here. We run a 3 MeV particle accelerator, which is similar to the machine I used to run in Kalpakkam, which is 22 years ago. And we do Rutherford backscattering spectrometry, look at the thin film thickness and stoichiometry, this is compositions. What it does is when ion beam it hits the material, it takes the scatters the mass. So if the higher the mass, it comes into higher energy. You can see bismuth and telluride and a silicon substrate. So this is useful to measure the ratio, stoichiometry ratio of the thin films. If you anneal them, also you can look at it. How does the annealing, stoichiometry changes with respect to annealing? What this diagram tells you is that we are able to tune the bismuth antimony concentrations and using this technique. So as a result, so what happened in the crystal structure? We managed to form an amorphous film when you form it, which is good. Then, depending on the annealing condition, we can crystallize them to a polycrystalline or crystalline. Which tend to suggest that you are playing with the grain size. And when you're tuning the grain size, you start up playing with the interplanar spacings as well. So you can estimate there must something happen to the crystal structure. So we looked at quickly what happens there. Then we also look typical like you all do. We look at the CM and EDAX to see if there's any impurities there. There's no impurities, and you can see whether it is a nanostructured or plain smooth films. You can see after annealing, it become a nanostructured bismuth antimony telluride, and it's even annealing 200, 300 to 400 degrees C. It's enough to nanostructure them, and also if you look at the distributions of these nanotextured films in the AFM, you can see the grain size and they're reasonably distributed after annealing. So in a net factor, so what? How does this relate to electrical conductivity? Because that's what matters for us. So we did the Hall effect measurements, and as you can see, we're able to improve the electrical conductivity depending on the annealing from 10 power 1 to 10 power 3, which is significant increase. And which, if you look at the Hall electron density and number of N, which is a key factor, if we look at the effective mass, carrier mass concentrations in the previous formula, they are reasonably within the error bars as well. So that's good. So this also shows that it is a N-type material, so it's N-type conductivity. What we produce, contrary to the P-type material reported in the literature, because we desperately made it under stoichiometry film. It's a tellurium rich in the ultracapacitor films, which plays the N-type behavior. So that's the difference from the previous results. Then we looked at, okay, so how does the Seebeck coefficient? Because Seebeck is squared. I always look at, can we really do something in the Seebeck? Because then you can increase the efficiency. So this case, you see, ultracapacitor has highest Seebeck coefficient, and annealing, the Seebeck coefficient went down. Then the simplest way to calculate the thermoelectric efficiency is called power factor, which is basically alpha squared sigma. So if you see the power factor, we are sort of saying by annealing somewhere between 100, 200, we actually get a high power factor, which can relate to the efficiency as well. So in summary on this one, we're able to make these films and under stoichiometric and over stoichiometrics. We can increase the grain size growth significantly by depleting bismuth, which obviously change the electrical conductivity and Seebeck coefficient. And these results are complementary to previous. But what we saw is we shown a different mechanism why power factor is increased due to the simple playing stoichiometric like that. So what we did after this, we applied to one of the heat exchanger plates. The reason I am not showing any picture is because it's commercially sensitive. But you have seen the diagrams I shown you from the introduction, where there is housed the heat exchanger plates where the thermoelectric films are underneath. Like I'm just going back a few slides. You will conducts here. You see, this is the thermoelectric. So what we did is here is we coated these films on this heat exchanger plates, because there's around 200, 300 degree temperature comes depending on where it is. So if you have a junction there, it can absorb the heat, and we are able to demonstrate that you can generate few volts, which can actually power even the nearby electricity network, like bulbs and the buildings. And that's still better than, because it comes from the free waste heat. So this is, so we have work with industries to demonstrate where the geothermal plants, where there's so much turbines running around, and also the manufacturing companies where they manufacture appliances and basically refrigeration systems and heat exchangers like that. So this is a kind of advantage if you work with thin films, because you'll be able to deposit immediately and demonstrate, and then that will give you feedback. Is there anything can be improved further? Because when you're talking about grind size and then it comes to adhesion as well, when you put in the heat exchanger. So we look at a bit more side. The next materials we looked at is zinc antimony. So that's again, that's a orthochromic structure, which is another interesting material, where we made it's basically a powder and films. So this case I'm presenting a zinc antimony film, which is a beautiful, again, composition analyzed by for backscattering spectrometry, where we can measure the thickness. Then we looked at the structural analysis again. We see the mixed phase of zinc 4sp3 and zinc antimony. So they are both observed commonly. So this is interesting, because some of the techniques can only do a single phase, and we are, by tuning some of our parameters, we can have a mixed phase. Then you can actually take one phase and reduce the other phase by annealing it. So if you look at the detail of this excited spectra, you can see we are able to manipulate differently by annealing it in just in the argon atmosphere, argon environment, basically. So this is the reason why we did zinc antimony. The zinc antimony is well known for medium temperature, so it's a high efficiency in somewhere between 200 degrees to 300 degrees Celsius. Because the bismuth antimony telluride, and bismuth telluride is quite good for room temperature up to 100 degree or 200 degree. Then if you go to the next temperature gradient, 200 to 400, that's where the zinc antimony comes in. And you can see this Raman spectroscopy, this one, even previous one, if you see there is 400 degree anneal, you can set a beautiful crystalline zinc antimony as well. As you can also see Raman peaks, where it confirms that it's a single crystal and strongly correlated to the stoichiometry of the zinc antimony. So this is again a kind of indication that we can tune the phase as well. So what happens in terms of conductivity? Again, we do simple Hall probe. We look at the conductivity. As you can see, if you anneal at 400, the conductivity goes up, and the carrier densities goes up, and the mobility is also going up. So you see, we are able to manipulate it, and this is when you see increased electrical conductivity more than 300 degrees, and simultaneously increase the charge carrier density and carrier mobility. This is great. So this is a kind of a top layer where you're looking for the efficiency. So we looked at a bit more again, Seeberg, which is key element, as I said before, and that's reasonably high, up to 200. When you anneal, Seeberg goes down. So, but we have to put it in the context of alpha squared sigma, which is the power factor, which is the combined thermoelectric efficiency, where even though you're losing a little bit of Seeberg here, but you're gaining huge in the conductivity. So the alpha squared sigma power factor is reasonably high for 300 to 400 degree. So there is a balance. So by narrowly tuning the electrical conductivity and the Seeberg coefficient, you can improve the power factor, which is related to the efficiency. So this is the other area. So in summary, this shows that you can actually achieve in a medium temperature thermoelectric materials as well by simply tuning the conductivities and Seeberg. So this is again, this only can achieve, actually you need to have a right phase, and by controlling the secondary phase is the way to go forward for this one. Right. This is all we know from that. Last year, I discovered a new concept which is just patented. Can we really harvest energy in your glass window? See, most of our houses have a glass window, and you have bloody direct sun hitting on the window. What can we do with that? Of course, we need you need a visible light to go through, because we want to see inside. You don't want turning on the bulb. So we want the visible light to go through. But what do you do with the UV light? You know, sun has got a 55% infrared. Visible infrared radiation is remaining visible in UV. Then there's so much radiation is available. So what we thought is, why don't we have a thermoelectric coating layer on the front of the outside window? Then you have create enough temperature gradient. I'm sure you're seeing the diagram. You know, everything okay?
Fine, Kennedy.
So you can see, without having a transparent thermoelectric coating, which means you should be able to still see through the visible light, but can you really capture the UV light and convert it into few volt, which is good enough to at least lighten the bulb inside the house, indoor. That's even better. So obviously, when you're talking about transparent, you need a wide bandgap material. So because now you're trying to play between transparency, the same term thermoelectricity. Well, and you can look at the picture as a glass window where thermoelectric films are coated as well. This is an interesting challenge. I got a discovery grant funded by Royal Society last year to look at this bit more in a new concept. So what we did is we looked at what are the transparent thermoelectric material available. So if you look at this diagram, you need to have a band gap about 3, somewhere between 3 to 4, because if you, in order to get the figure of merit high, you need to have high Seeberg coefficient electrical conductivity, and you also have to reduce the thermal conductivity. Then you have to maintain the optical transparency. So there is a materials proposed are copper iodide, copper aluminum oxide, and even aluminum zinc oxide, which comes under that kind of region band gap. So we started looking at it. Can we really make these materials in thin film and deposit in a glass window and see how much energy we can harvest? So we first started with the zinc oxide. Everybody knows zinc oxide. It's a beautiful crystal structure. There's a lot of work been done in zinc oxide for various applications. And so it's easy to dope it, and you can have when you make a zinc oxide flames, it forms a preferential orientation of C-axis, which is easy to manipulate, and you can anneal in air or vacuum, and you can tune the crystal structure. Its transmission is more than 80% in the visible region. So these are transparent as well. That's the beauty. So then we thought, okay, in order to improve the carrier concentration, so let's dope aluminum tiny. So we doped 1 or 2% aluminum. We use our favorite technique called ion implantation, which is what I did during my PhD days, to dope iron aluminum into zinc oxide thin film in this case. So what happened? Yes, the aluminum is inside the material. You can see by looking at the peaks broadening, and you can see aluminum doping effect. So let's get into the real one, conductivity. So what happens when you have aluminum zinc oxide? Can you really tune the conductivity? You can see that we are able to change the conductivity by having 1 or 2% aluminum concentration, and the carrier concentration is reasonably stable. So the mobility is changed slightly as well. So this means you can actually change the conductivity nicely, and we are maintaining the increase in conductivity. Reason is due to the increase in carrier concentration and electron mobility. So when you go to Seeberg and the electric conductivity together as a power factor, we are able to increase it as well. So the reason why we picked up zinc oxide is it's used to apply in the industrial application because it's a cheap material, it's oxide, and you can easily make thin films by either sol gel, any chemical processing technique or any thin film techniques. And so we wanted to see how do you manipulate the power factor so that this could be used as a transparent. And the efficiency is very low. And so that's the reason why zinc oxide it's not successfully commercialized, because you can dope. If you dope too much, then it will become too high conductive as well. The carrier concentration goes too high, which means you will lose the seabed. So we're able to tune it optimal range. This one we put it under the similar coating on the condenser. We found that if you coat these films over 1 meter, we're able to generate 5 volt, which is still not bad, but it shows that at least you can use it. But in a glass window here, you have a UV light. You have to dense them over the temperature gradient, so you really need to have high efficient. So what we did is we looked at the copper iodide, which is really interesting because they have copper iodide is a P-type thermoelectric material. So the crystal structure is polymeric phase. It is a zinc blende structure similar to the other one, and it is predicted to have a figure of merit. It's more than 0.2 at room temperature. 0.2 is still high relative to other organic materials, but it's not like 1 like bismuth telluride. But we thought, let's see whether can we do something here with the nanostructured form, because you have a large surface area, which might help in a glass window where when you deposit these flames, which might help to recover these phonon scattering and thermal conductivity issues. So the literature clearly says gamma phase copper iodide that's what you need in order to have a transparent and thermoelectric as well. So we did flames again as usual. We always make thin flames. We do RBS to measure the compositions by astapositor and annealing. Then we look closely. How does the microstructure look like in the TEM? You can see we found that there's some copper metal precipitates forms after annealing as well, which they are very tiny nanos. As you can see, they are less than 10 nanometers, some of these precipitates, if you see in the figure 200 degrees C, and they are tiny, like 5 or 2 nanometer precipitates. So that's interesting that it's kind of metallic precipitates in your systems. We looked at very closely Raman to always make sure it's still maintain the crystal structure. It's beautifully maintained. And we also looked at the XRD, that's still the same structure. Then we used the synchrotron XAN studies, exact studies to look at whether copper 2B states and 3D states, look at whether either these precipitates are visible or can you have some sort of density of state, defect states basically. So when you look at the pre-etched features of copper 2B, suggests that copper metal like a defect state, then the shift of transition peaks, the annealed films indicated that there is a definite difference in the structurally. So that tend to say that, okay, this must have some influence on the electrical conductivity. So this one you can look at very closely, the electrical conductivity and mobility and the carrier concentrations, they are very good in the astropacitors. So this means this could be a very good perfect room temperature to maximum 100 degree or 50 degree. So this is interesting research we got on the transparent one. Obviously, seabed, it's actually quite good for 50 to 100 degree, which is what the maximum heat you can anticipate in a glass window if you cover them in a large area. So as I said, when you look at the power factor, which is directly related to the efficiency, it was really high, from room temperature, like say 50 degrees to 100 degrees C. This is again off the press. This is just the paper is just accepted in applied energy materials. So this is again the new results I'm presenting here. But what it shows that we're able to have a material which is transparent 100%. I mean, it's 90% transparent. At the same time, have reasonable seabed. So thermoelectric efficiency. So then we try to explain the seabed coefficient related to carrier density. because there is a feature called energy filtering between the interface of grain boundaries of copper iodide and metallic copper. And when you look at a bit more closely with the band diagram, and you can see that the low and high energy difference, which is from the Fermi energy to the D band, and you can actually tune the bending, we call it band bending, and the high energy goes, which is reflecting that there's a high Seeberg coefficient if you have a carrier density somewhere between 1 and 1.5. So, which is the curve is the effective mass concentration. As you remember, that's M star, which is directly proportional to the Seeberg coefficient. So that's something we have been trying to fit with the theory and explain why we got the high Seeberg coefficient. So as I said, transmission is good. You can actually go up to 80%, in some cases even 70, 90%. And we did a thorough study. You can see on a picture here on a glass substrate, there you can still see through the glass, but it's actually there is a 2 nanometer copper iodide film on it. So that shows you visibly it's transparent. And this is again beautiful results, because if we can optimize, improve the transmission, you take the waste-free energy from sun and through going through UV, through your glass window, and you can harvest them. So this is the area we are currently concentrating to optimize. Can we really get a high efficiency factor? So we are also doing a lot of doping effects. I think to look at a bit more on you can dope in antisites and lattices. This is done with our US collaborators. I think because of time, I'll run through this one first. And so in conclusion, we can say that nanostructured thermoelectric films, by making a simple thin film techniques, can give you a high power factor, which is related to thermoelectric efficiency. We looked at it various temperature regime materials, room temperature and medium temperature, and even high temperatures as well. And we are able to tune some of these key factors of electrical conductivity and Seeberg coefficient. And this is again done in a multi-institutional collaborative way, because it needs a lot of techniques to understand better. And so we are running a collaborative program which combined with the PIs from many countries. So with that, I'll see whether my next movie play or not. If it plays, tell me, Vinod, are you hearing or not? Can you hear it? Vinod, can you hear the sound?
Yeah.
So this is to show you how beautiful New Zealand. You are most welcome to visit here as well.
Thank you, Kennedy. Thank you very much. So can you take few questions?
Yes, I can.
The session is open to questions. Please feel free to ask questions.
They can also type in the comments. I can pick it up from the comments.
Okay.
And then you are asking a question?
Okay. I think Kennedy is knowing me.
Yep.
Professor Kennedy, I am Pradyumnan.
Yes, how are you?
Remembering me?
Yes, I remember now.
Okay. Actually, we people are now doing mainly concentrate on thermoelectric materials. I think you might have heard out maybe through our papers sometimes. Okay. I have no doubt on these particular transparent conducting, transparent thermoelectric materials.
Yeah.
What about the, can you hear me?
Yes, I can. Go ahead. Please go ahead.
What about, what about the stability of this copper iodide? Because you are placing this particular material on a surface, it is outside and it is always in contact with air and etc. So what about
Yeah.
the humidity and other things will be, because it is an iodide material, so not like oxides.
Question. It's a good
Yeah,
question.
yeah,
Copper iodide doesn't get oxidized easily.
yes,
So that's the one beauty of it.
yeah,
And because most of the time it depends on how the film is deposited on a window. If your adhesion is poor, if your films are porous, obviously it will respond to humidity. If
yeah,
your film can be smooth and nicely stick to together like adhesion, and it's doesn't matter, because then one would ask a question: what about the rain? Yep, it's a practical concern. It's a good point. So this comes in again when it comes to, depending on how the building is. Some places you always have a thing on the top so the rain doesn't really hit the glass. But ideal scenario, we are talking about no rain. Okay, so because when the moment you come more vapor formation, obviously that will penetrate through eventually if your film is not stable. If it's not smooth and well prepared. So ideally, this is good for a place where it's exposed to sunlight but not directly to the rain at the start. Even
yeah,
if it is raining, you can think of a smart window like a perspex or something to the front, which does not stop the UV. Okay, you can still transmit through. So it depends on the design. End of the day, it comes to design, but it doesn't oxidize easily, so it's okay. But again, the other biggest advantage is you are talking about 0 to 50 degree, which is the temperature you're living. Especially in India, we are living in 30s to 40s, right?
yeah,
So that temperature, it will be deposited anyway. And this is more effective somewhere between the 50 to 100 degree. So it's a low heat in a way. It's also depending on the insulation. When I say glass window, of course, you need to have insulating area in between before the inside. Because you need delta T. You need a temperature difference to convert the voltage. So you have to create a temperature difference. So one side you see hot, one side you get cold. Cold is your house inside. So you need to have a barrier, and that's how the design works. In here, we are living in a cold country, it doesn't matter. But it's possible to design that way. As I said, this is again copper iodide. You've probably seen the papers are only coming in the last 3 years. As you probably know, it was not before. So this is one of our early discovery work. We are now trying to see if we can really somehow increase efficiency. Then it is an engineer's problem to see how to design and capture more the heat in the window.
yeah. And also in oxide materials, what about oxide materials? You are not explained not much, only in
So
the case of zinc
oxide
oxide.
materials, we looked at only zinc oxide.
Yeah,
Zinc oxide is good, but the oxide materials, like you say, stability is a problem. And then it's exposed to similar scenario,
yeah,
but the efficiency reach to the point it can't go more than 0.1, 0.2, because if you put too much aluminum, your number of carrier concentration goes high, so you're not winning, because you don't want the carrier concentration too high as well, because aluminum is a metal. So if you put any metal, your carrier concentration goes high, and so you need to reduce the thermal conductivity. Reducing thermal conductivity is one of the biggest challenges,
in oxide case, we need more temperature. So temperature gradient is
Yeah,
high.
I'm
Yeah.
talking about transparent context, but
Okay.
oxide good for high temperature purpose. So if you put in transparent thermoelectric contacts, oxides are okay, but not as good as the other ones. But if you go to 400, 800 degrees Celsius, oxides are perfect.
Okay. Okay, thank you.
Any other question? Libu?
Yeah, it's okay. I'm allowing.
Hello, any question?
It's probably they're challenging because they're all at the work. They're all
Hello, sir.
traveling home. Yeah, go for
Hello,
it.
sir. I am Shabir.
Okay, go ahead.
Hello, sir. I am Shabir. I am doing PhD under Professor P.P. Pradyumnan.
Yes.
Now, I have a doubt about your copper iodide nanostructuring. You have mentioned nanostructuring of copper iodide, and you enhance the band gap and the SIBO coefficient.
Yes.
At the same time, nanostructuring also increases the resistivity of the material. How can we optimize this resistivity and SIBO coefficient enhancement to get a high power factor?
Yes. So that's a good point. I think if you am I still presenting? You can see my slides.
Yeah.
We can.
No,
It
slide
is coming.
It is,
can't
you
see
can
the
go to
slides?
the slide.
Can you see the slides?
Okay.
Yes.
sir.
So this is the slide you're after. You see, this is the kind of interesting thing. Up to 100, 150 degrees C, you can actually the electrical conductivity is it's going down obviously when you anneal longer. But as I said, copper iodide is mostly for good rust capacitor and up to 100 degree Celsius. So you need to find the phase, proper phase, to be able to have a stable and reasonable conductivity and SIBO coefficient. And if you see mobility stays in, you see the blue line, which is a good sign, so is that it's good. Mobility is not changing. It's only your carrier density is changing, but it's not much if you take it from mass capacitor to 100. While your carrier density is changing, your alpha is also changing. Your sigma is also changing. So, but if you put in a context to the power factor, it's still not big difference. Yes, it's very hard to control the conductivity, I agree. And that only way to control conductivity, you control the grain size. And that's the biggest challenge we are facing. Does it make sense?
Yes, sir. Okay, sir. Sir, one more doubt. Usually, nanostructuring decreases the transmittance of the material.
Yep. It's a good question. So this is why.
Then, when we nanostructuring this thin films for a transparent thermoelectric material, when we increases the band gap by nanostructuring, does it decrease the transmission?
You look at this diagram. When you have a band gap, as capacitor is 3.05 to 3.06, that's insert. If you look at the transmission diagram, can you see it?
Yes, sir.
And when you anneal longer, the band gap is going down. And
3.06 to 3.
Yes. So this is when you anneal too much, these nanoparticles become larger. Okay. And when you become more agglomeration, and it's no longer, it's really the surface area is, you're starting to get more voids. So it's quite good for up to 100 degree, 100, I mean maximum 100 degree, I would say. But the beauty is the transmission still stays, because you have to maintain transmission as well. Otherwise, your visible light cannot go through, right? So you need to find the balance there. Yes, band gap does changes when you anneal a high duration of time.
Okay, sir. Thank you.
And which technique you used for this preparation copper iodide? Is it sputtering?
Yes, we use ion beam sputtering. Our first paper is just coming out in advanced energy materials. Wait on a couple of weeks, it will come out. Initially, because we work with the industries, we always do the patenting first, then we go for paper. So this is always, that's why we don't publish many papers, and sometimes on some areas because it's commercially sensitive.
Okay, good.
Questions? I appreciate students' questions. So if any other students want to ask questions, please. No? Teachers also can ask, sure. Okay, if there is no question, let us thank John Kennedy for very nice talk. So we are very happy that you could come on this time and start this program. So thank you very much. And,
Thank you, Al. It's nice to see everybody.
and I request you, whenever you are coming visiting India, let us know so that next time you should be able to even present here in the university.
Yeah, next time I'll
invite you on the question.
Definitely next time I will fly to Calicut.
Sure. Thank you very much.
Because most of the time what happens, I fly to Trichy. Trichy is my closest airport to my hometown. Trichinopoli, you know. So then from Trichy, it's only 2 hours drive to my village. So that's how I go. So I don't come to the other side.
Okay, sure. No. Okay, so let us wind up this program, and thank you again, and thank you everybody. All. Thank you. Bye. So today evening we have one more seminar, and I invite everybody, and I hope everybody should join before 7 p.m. Okay, thank you.